All right, I have 10:30, so let's start. I returned assignment 1 to you yesterday, and I posted solutions. Usually, I wasn't planning on writing solutions in this course, but because I've been trying to figure out the problems myself, I might as well share them with you. And I do have solutions to assignment 2 ready, so I will post those quicker than before. Assignment 2 is due tomorrow night, I think. I will post. I want to post assignment 3 tomorrow. I might only be able to post 2 or 3 problems out of 5 tomorrow, and then the rest by the end of the week, but that's probably okay. And the plan is that it's due 2 weeks from tomorrow, but it might end up being like 16 days or something like that. We'll see, because there are 5 assignments in total. The 4th one will definitely be due before the last day of lectures, but the 5th one will probably be due a week into the exam period, which I'm allowed to do because there's no exam for this course. Yeah. Yeah. I can't remember exactly what the question says, but if it's a map between 2 vector spaces.
It's from the epsilon ball at 0 to the epsilon ball.
There it's the same, right? You're saying from here to here. If this is a normal ball, then being an isometry in the Riemannian sense is the same as the metric space sense. Yeah, but I mean the Riemannian sense. Yeah. Okay, so the last thing we did on Wednesday of last week was state the Cartan-Hadamard theorem, and we're going to prove it today. Then maybe we'll move on to other things. So this is our first non-trivial global result, and whenever we're going to prove a global result in this course for the rest of the term, almost always, I think always, we're going to assume that our manifold is complete. Our Riemannian metric is complete. Right? Without completeness, you don't get nice global conclusions. When we prove some local results, which we'll still do, especially at the end of today or on Wednesday, local results don't need any notion of completeness, right? But the global results will always either assume completeness or a stronger property like compactness. So this was the theorem. Let MG be complete. That means the Riemannian metric is complete, which we know that means equivalently the metric space distance function makes into a complete metric space. Complete, simply connected, that's a topological condition. Means the fundamental group is trivial. With sectional curvature non-positive everywhere. So for all P in M and for all 2-dimensional subspaces of TPM. So all the sectional curvatures at every point and in every 2-plane at that point are not positive. Of course, we're not assuming it's positive, it's constant or anything like that. Then the exponential map, which we know is defined on all of TPM because the manifold is complete, is a diffeomorphism. So in particular, because TPM is diffeomorphic to Rn, M is diffeomorphic to Rn. Okay. So any complete, simply connected, non-positively curved Riemannian manifold has to be at least diffeomorphic to Rn. We're not saying it's isometric, right? The metric doesn't have to be flat. And there's an example already that we know of this, which I didn't really go into at all, but the hyperbolic, n-dimensional hyperbolic space is complete and it's negatively curved everywhere. The sectional curvature of it is constant and negative. So this theorem applies. And once you know that the hyperbolic space is complete, which you can show. So the hyperbolic space is diffeomorphic to Rn, and there are various models of hyperbolic space. One of them is the upper half plane, upper half space model. That's the upper half space is diffeomorphic to Rn. Another one is the open ball model. The open ball is diffeomorphic to Rn. Right, so you can see this theorem in action for hyperbolic space. Okay, so to prove this, we need 2 lemmas. The first one is really where we use the non-positive sectional curvature. And the second one is a more general result that we're going to we're going to use again later in the course. So I'm going to call them H1 and H2 for Hadamard. So let MG be complete with non-positive sectional. That's exactly this condition there. Then for any P and M, the conjugate locus is empty. Is empty. Okay. That means, remember, what does this mean? I.e., for all, for any geodesic gamma joining P to Q, which is not equal to P, there does not exist. Q is not conjugate to P along gamma. And remember, what does this mean? This means there does not exist any non-trivial, non-zero Jacobi field along gamma with vanishing at the two endpoints. That's what a conjugate point was, right? A point is conjugate to the initial point of a geodesic. A point on the geodesic is conjugate to the initial point if and only if there exists a Jacobi field along that geodesic, which vanishes at those 2 points, but is not identically zero. Thank you. Does not exist. Okay, so let's prove this lemma. Oh, before I prove it, yeah. Is it? Okay. I put this on the assignment? No, yeah, you should. I'm going to do it again anyway, because I've not, yeah, I don't remember putting on there. I believe you. But I took the assignment questions from the exercises in DoCarmo, and I'm taking this from DoCarmo. So unless that appears in another part, yeah, maybe it appears in an earlier part of the textbook. He does that sometimes. He lists things as exercises earlier on, and then he proves them later in the book. That could be, but let's do it anyway. But in particular, what does this say? This says that the exponential map, which we know is defined on all of TPM because it's complete, this is a local diffeomorphism. So why is this? Why does this follow? Because since there do not exist any conjugate points to P along gamma, along any geodesic gamma emanating from P, we get that the exponential map push forward, xp push forward at V is invertible for all V in TPM. Because of the characterization we had of conjugate points, we showed that gamma x, so recall xp TV, or let's say V, is a conjugate point to P along gamma of T is xp TV, if and only if the push forward at this point is singular. This was from last week. Okay, so since there are no conjugate points, that means the exponential map push forward is invertible at every point. And that means by the inverse function theorem, this implies that XP is a local diffeomorphism. So you can see that this lemma sort of gets us part of the way to the Hadamard theorem, because we want to conclude that the exponential map is a diffeomorphism. Local diffeomorphism is a good start. So I was just told this is on the assignment, but let's give a proof anyway. This is not the proof that's in Do Carmo because I don't understand his proof. He leaves out a lot of details. So suppose J is a non-trivial, that means not identically zero, Jacobi field along a geodesic gamma. And the geodesics are defined for all time because the manifold is complete. So where gamma of 0 equals P, J of 0 equals 0, and J prime of 0 is not 0. So why can't I assume J prime of 0 is not 0? Because we know that the Jacobi field is uniquely determined by the initial data. So I want to get a contradiction to the existence of a non-trivial Jacobi field vanishing at 2 points. So it has to vanish at the initial point. And if the initial covariant derivative also vanished at time 0, then it would have to be the trivial Jacobi field. So this is because J is non-trivial. Non-trivial. Okay. So we need to show that J of T is not equal to 0 for all T. Okay. So let's compute the second derivative. This is 2 J prime plus 2 J double prime J, and then by the Jacobi equation, plus minus 2 R of J gamma prime J. And this is greater than or equal to 0 since K is non-positive, right? I've multiplied by -1, so this is greater than or equal to 0. Of course, if J has a component parallel to gamma prime, that part is 0 anyway. So I mean, really, what am I doing? I'm saying that this guy is equal to K of the 2 planes spanned by J and gamma prime times that thing. And this is greater than, this is greater than or equal to 0, this is less than or equal to 0. And then I have a -2. Okay, so the second derivative of that is non-negative. And let's let phi of T be J of T, inner product J of T. What have we shown is that phi double prime of T is non-negative for all T. Phi of 0 is definitely 0 because J vanishes at time 0. And what about phi prime? Well, that's 2 J of T, J prime of T. And this is also 0 at time 0 because there's a J here. Okay. And what do we know about phi double prime at time 0? This guy is always non-negative, and this guy is strictly positive because the initial covariant derivative is not 0. This is strictly positive. Okay, and then that's it. Let's see why that's it. Let's write down Taylor's theorem, integral form of Taylor's theorem. We have phi of T is phi of 0 plus T times phi prime of 0 plus the integral from 0 to T of T minus S phi double prime of S ds. And if you never saw this before, just take this guy, integrate by parts twice, and you'll get this. And this guy is greater than or equal to 0. And this is 0, and this is 0. Okay, so that means that phi of T is greater than or equal to 0 for all T. Suppose that phi of some T naught is 0 for T naught positive. Then because the integrand here is non-negative and it's continuous, this implies phi double prime of S is 0 for all S from 0 to T naught. but phi double prime of 0 is positive. Okay. So the non-positive sectional curvature and the completeness, we use the completeness here, right, to be able to go all the way up to infinity. The non-positive sectional curvature and the completeness implies there's no conjugate points, and that implies that it's a local diffeomorphism. Okay, so let's look at lemma 2, which, as I said, is going to be much more general than what we need to prove the Hadamard theorem, but it's useful later in the course, so that's why we're going to prove the general version of it. Lemma H2 let MG be complete and let F from M to N be a local diffeomorphism where NH is a Riemannian manifold. So I have a smooth map from MG to NH. G is complete. I don't care whether H is complete or not. And this is a local diffeomorphism such that for all P in M and all V in TPM, if I look at the push forward by F at P applied to V and take the norm there, that's greater than or equal to the norm of V. So here, this is a norm on T F of P N using the metric H at F of P. And this one is on M TPM GP. Okay, then F is a covering map. Okay, so I'm hoping that you know what a covering map is from topological spaces. If you don't, just don't worry about it. I mean, I'll tell you what it is in the course of the proof. So I want to give these numbers. So this is hypothesis 0. Local diffeomorphism is hypothesis 1. And this guy is hypothesis 2. So we can see where we're going to use everything. Okay. So let me tell you what we're going to prove, and there's some theorem in topology that tells you that this is equivalent to being a covering map. And if you want, you can just take that as the definition of a covering map. So by the general theory of covering spaces, it suffices to show that F has the path lifting property for curves in N. What does this mean? It means the following, that whenever we have a smooth curve in N, and we choose a point in M that lies above, that's in the preimage by F of the initial point in N, then we can lift it to a curve. So this means whenever alpha is a smooth curve in N, and P is a point in M such that F of P is alpha of 0, then there exists a smooth curve alpha tilde on M such that alpha tilde of 0 is P, and F compose alpha tilde is alpha. Okay, so I'll draw a picture. As I said, if you've never seen a covering map before, you can take that as the definition. Let me draw something that looks like this. This is M. So I have a curve alpha. And I choose some point P that is sent to alpha of 0 by F. Okay. Then it's the covering map if I can find a curve alpha tilde so that P is alpha tilde of 0. This is alpha tilde of 1. And F of alpha tilde of T is alpha T for all T from 0 to 1. This means that this curve lies above the yellow curve. Okay? And if I chose some other point, Q, let's say there's another point that is also sent to alpha of 0 by F, because F does not have to be injective, then there'll be some other lift here, alpha double tilde. Okay, where alpha double tilde of 0 is Q, and F composed alpha double tilde is alpha. Okay. So the definition of covering map is that every point in M has an open neighborhood which is mapped homeomorphically onto its image in N and some other technical stuff. And it's equivalent to this path lifting property. Okay, so you can look it up in some algebraic topology textbook. But we're going to prove that if we have these three yellow conditions, then we have this path lifting property. Yep. Mm-hmm. The base space doesn't even see, you need probably locally path connected and locally simply connected. Yeah, and manifolds are always like that. Yeah, yeah. And the connectedness is a global thing. Okay, so proof. Okay, let's define A to be the subset of times from 0 to 1. Oh, sorry, I already started writing proof, right? So we'll show F has the path lifting property. So let alpha be a path from 0 to 1 in N, such that alpha of 0 is F of P. So let P be a point in M, and let alpha be a path in N whose initial point is F of P. Let A be the times such that there exists a lift alpha tilde of alpha on 0 up to T. Okay, so this is a subset of 0, 1, and it's not empty since 0 is in A. So we're going to show that A is open and closed in 0, 1. We'll show A is open and closed in 0, 1. And that implies that A is 0, 1 because that's a connected space. And I have a non-empty open and closed set. It has to be the whole thing. Okay, so we need to show openness and closeness. Yeah, openness openness is really just going to follow from the fact that it's a local diffeomorphism. Closedness is where we're going to really need to use this property. I'm going to have to skip this board because I don't want to erase these things. So claim A is open in 0, 1. So let's let T naught be in A. What do we need to do? We need to find an open neighborhood of T naught in A, which is contained in A. Okay. So alpha tilde exists on 0 up to T naught. Since F is a local diffeomorphism, this is assumption 1. There exists some there exists some U containing alpha tilde of T naught open, such that F restricted to U is a diffeomorphism. And alpha of T naught is F composed alpha tilde of T naught is in F of U, which is open in N. This is open in N. That's what it means to have a local diffeomorphism. I'm going to keep that on the board. So by continuity of alpha, it's a curve. It's a continuous curve. There exists some delta such that alpha maps the interval, the open ball around T naught intersects 0, 1 into F of U. Right? Because this is an open set in N, and this is a point in that open set. So by continuity, I can, as long as I'm close enough to T naught and in here, because it's continuous on here, then alpha will send that open set in O1 into this open set in N. And now let's define alpha tilde to be F restricted to U inverse compose alpha on T naught minus delta, T naught plus delta intersect 0, 1. Okay, so so this agrees with the original lift alpha tilde on the overlaps, because F restricted to U is bijective. Okay, so at the points where we have two different definitions of alpha tilde, they agree, and by construction, F composed alpha tilde equals alpha on T naught minus delta, T naught plus delta intersect 0, 1. So I can go all the way up to T naught plus delta in the lift, hence A is open in 0, 1. Okay, I was going to say something here. Yeah, this is true because you just apply F to both sides, right? You get F composed alpha tilde is off. Okay, so the next claim is A is closed in 0, 1, and that would complete the proof. So this is where we're going to have to use, all I used here was the local diffeomorphism. We're going to have to use completeness and the assumption about the push forward of F there. This magnetic thing seemed like such a good idea when they did it. Not really. Okay. Okay, so let's let tk be a sequence in A, such that the limit as k goes to infinity of tk is some t infinity. And of course, that has to be in 0, 1, because this is closed. So we need to show that t infinity is in A. So alpha tilde of tk is a sequence in M, right? We have our alpha tilde is defined for all times t in A. And let's look at L is the length of alpha Well, what's that? That's the integral from 0 to 1 of alpha prime t dt. But that is going to be greater than or equal to the integral from 0 to tk of alpha prime t dt. I'm just taking the length on a possibly smaller interval. And this, because f compose alpha tilde is equal to alpha on 0 tk, we get 0 to tk f compose alpha tilde prime of t dt. And then how do I compute the velocity of this composition curve? This is equal to the push forward f star at alpha tilde of t applied to alpha tilde prime of t, the length of that, dt. And now we're going to use assumption 2. Right, that the length of this pushed forward is greater than or equal to the norm of alpha prime of t. dt. What have I done? Alpha tilde prime. Okay. And that, of course, that's some curve from alpha tilde of 0 to alpha tilde of tk. So this can't be any bigger than the distance between those 2 points. Okay. So by using property 2, we've shown so the distance from alpha tilde of tk to alpha tilde of 0 is less than or equal to L for all k. Okay. So the sequence alpha tilde of tk lies in the compact set the metric ball of radius L centered at alpha tilde 0. And why is this compact? This is by completeness, right? We're assuming that M is complete. And we know that in a complete metric space, the closed balls are, this is the closed ball, are compact. Okay. So I think I can erase the hypotheses now. So alpha tilde of tk has a convergent subsequence. So we get alpha tilde of tkl goes to some q as L goes to infinity, q and m. Okay, and now let's use again the local diffeomorphism property. Let V be an open neighborhood on which f restricted to V is a diffeomorphism. This is again hypothesis 1. And what do we have? We have alpha of TK is f of alpha tilde of T, let's put TKL. And this goes to f of Q, which is in f of V, and this is by continuity of f. Okay. So this is all happening in N, but an N doesn't have to be complete. I don't care about that. It's still a metric space. And this one goes to alpha of T infinity. Okay. So as L goes to infinity by continuity of alpha. So alpha of T infinity which is equal to f of Q, is in f of V, again, by continuity. There exists some interval T naught minus delta, T naught plus delta, such that alpha of I intersect 0, 1 is contained in f of V, and choose L sufficiently large such that alpha of TKL is in V. Take the lifting beta of alpha on here using beta is f restricted to V inverse compose alpha. On the overlaps, they agree. Beta agrees with alpha tilde, since f restricted to V is bijective. So beta is an extension of alpha tilde. Hence, alpha tilde is defined at T infinity. So T infinity is an A. Okay, so that's the proof of lemma H2. I have a feeling that I made the last part more difficult than it needed to be. As I was writing it, I think you can probably shorten it a little bit. Okay. Any questions about the lemma before we now use both these lemmas to prove the Cartan-Hadamard theorem? Okay. So as I said, you may not know what a covering map is. Hopefully most of you do, but it basically has this path lifting property. And the important fact from topology, if F is a covering map between topological spaces and pi 1 of M is trivial, this implies F is a homeomorphism. Okay, if you have a covering map from a simply connected space, then it has to be homeomorphism. So I'm going to use that here. So proof of Cartan-Hadamard. Okay. So remember the statement said, let me remind you, we have M complete, MG complete,
Question.
non-positive. Yep.
Shouldn't
Yeah.
shouldn't the condition be pi 1 of n is trivial?
No, I was thinking exactly the same thing. Oh, you're right. Sorry, you're right. Thank you. Thank you. It should be yeah, I got confused because I'm going to apply it to M in this theorem, but in this theorem, this is going to be TPM and this is going to be M. That's right. So if the
You
base
could have a
is simply-
circle, you know, a line wrapping around
Yeah.
a circle, which is a covering
Yeah.
map.
You're absolutely
That
right.
would
The
be
base
morphic.
has to be-
Yeah.
Okay. So remember the statement of the Hadamard theorem says if we have a complete Riemannian manifold, non-positive sectional curvature, and simply connected, then the exponential map, which goes from this vector space to this manifold, is a diffeomorphism. That's what we want to prove. Okay, and we have the two lemmas that are as our toolbox. Okay, so since MG is complete, we know that the exponential map is defined on all of TPM, and it's surjective. Right? One of the consequences of being complete was that any 2 points can be joined by a minimizing geodesic, not necessarily unique, right? So i.e., for all Q in M, there exists a normalized geodesic gamma from P to Q with Q equals XP of L V, where V has length 1 and L is the distance from P to Q. Okay, we proved this right before we did the Hopf-Rhino theorem. We showed that if the exponential map was defined for all time at a single point, then any point can be joined to that initial point by a length minimizing geodesic. Okay, so the exponential map is defined on all of TPM. It's surjective. Since K is non-positive for all P and for all two-dimensional subspaces of TPM, lemma H1 tells us that the conjugate locus of P is empty. So the exponential map is a local diffeomorphism. Remember, a consequence of lemma H1 was that the map was a local diffeomorphism. Okay, so now let's define a Riemannian metric XP star G on this manifold. This is a vector space, a finite dimensional vector space. I'm putting a Riemannian metric on it. By pulling back, I have a local diffeomorphism. It's a smooth map. I can pull back any metric on the target to a smooth 0-2 tensor on the domain. And remember, you proved in assignment 1 that if I pull back by an immersion, I get a metric. A local diffeomorphism is an immersion, right? When the dimensions are the same, being an immersion is equivalent to being a submersion, is equivalent to being a local diffeomorphism. So this is, note, this is not the constant metric GP, right? This is a vector space, and we have an inner product on there, which is the metric G at the point P, but I'm not doing that. I'm taking this local diffeomorphism and pulling back the metric here to a variable metric here. Okay. So by construction, the map XP from TPM with this metric to M with G is a local isometry. Right? It's a local diffeomorphism from lemma H1, and now we've given it the Riemannian metric that it needs to have for this local diffeomorphism to be a local isometry, because every point in here has an open neighborhood, which is mapped diffeomorphically onto its image there. And we've defined the metric in the domain to be the pullback by this map of the metric on the codomain. So it's an isometry on the, when we restrict it to a domain on which it's a diffeomorphism, it's actually acting as an isometry. Okay. So hence, f, which is x of p, satisfies that f star p phi equals v for all v in TPM. Let's do the f star w for all v in t in for all w in TPM and for all v in the tangent space to TPM at w, which is canonically TPM. Right. So this is my initial manifold is this vector space TPM. So I want to look at the push forward of this map at some point in the domain, and it has to act on a tangent vector at that point to the domain, but that's just TPM. Okay, so this is condition 2 of lemma H2. For lemma H2, all we needed was a greater than or equal to here. Right? It was more general, but here we actually have equal. And we have local diffeomorphism. That was condition 1 of lemma H2. And we also have complete. Oh, no, I have to show that. I have to show that it's complete. Okay. So I claim that TPM with this metric, XP star of GG, is complete. Okay. I know that M is complete. So this is true because the map alpha of t is t times v maps to xp tv under xp, and this one is a geodesic on M emanating from P, and it's defined for all time. For all t in R. And hence, since xp is a local isometry, it follows that alpha is a geodesic on TPM with this metric for all t in R. So what am I saying? This map XP is a local diffeomorphism, right? It doesn't have to be a diffeomorphism. But I know this curve is defined for all time in TPM. It emanates from the origin. And I claim that this is a geodesic in this Riemannian manifold. And the reason for that is because if you take any point there, there's going to be a neighborhood of that point that's mapped isometrically by XP onto its image. And on its image, it is a geodesic, right? And a local isometry will take geodesics to geodesics. The property of being geodesic, of satisfying the geodesic equation, is a local property. So hence, the geodesics of this Riemannian manifold with this metric emanating from the origin, are defined for all time. Right? Because this curve is defined for all time. And I showed you that it's a geodesic because locally its image under a local isometry is a geodesic. Therefore, that Riemannian manifold is complete. So hence, TPM, this vector space with this non-constant metric on it, is a complete Riemannian manifold. this was a corollary of the Hop-Rhino theorem when we observed that in order to prove geodesic completeness implies completeness, which in turn implies geodesic completeness, we only really needed the exponential map to be defined on all of the tangent space at a single point. And we have that here. Okay, so if we look at this map, to MG, we have that this is complete. We have the estimate equals V. This was condition 0. This was condition 2 for all W in TPM and for all V in TW of TPM. And we also have 1, F is a local diffeomorphism. That came from lemma H1. So we can apply lemma H2 to this situation to conclude that it's a covering map, and then we're done. So lemma H2 applies. This means that XP from TPM to M is a covering map, but M is simply connected. That implies that XP is a homeomorphism, but it's a local diffeomorphism. Well, that implies that it's a diffeomorphism. Okay, a local diffeomorphism that's a homeomorphism is a diffeomorphism. Okay, so that's the proof of the Cartan-Hadamard theorem. I want to make one remark, which is that we've actually proved something slightly stronger. Because if you think about it, where did we use the condition of being non-positively curved? We used it to apply lemma H1 to conclude that the map was a local homeomorphism. So in fact, remark, we've actually proved something stronger. Which is the following. Let a point in our Riemannian manifold be called a pole if P has no conjugate locus, has no conjugate points. In other words, C of P is empty. Okay. So if the sectional curvature is non-positive, then C of P is empty for all P. Okay. But there do exist poles in non-compact manifolds which are not non-positively curved. Okay, so they might have some points and some two planes at which the sectional curvature is strictly positive, but still they might have at least one point which is a pole. We proved if MG is complete, simply connected, with a pole, then the exponential map P from the pole is a diffeomorphism. Because that's all we used. We used that this was a local diffeomorphism. I'll get your question in a second. And it follows it's a local diffeomorphism if we know that it has no critical points, and that follows if it has no non-trivial Jacobi field starting at P that vanish at some other point, and that is equivalent to having no conjugate points. So in particular, M is diffeomorphic diffeomorphic to Rn. But you don't need the stronger assumption that it's non-positively curved told us that every point was a pole. But for the proof, we only needed one point that was a pole to get it to work. Question. Compact. CPT is compact, non-compact. So yes, to get an example like this, you need non-compact. Is it obvious to me why? It's not obvious right now why, but there are examples. Anyway, we're not going to use this stronger result. No, it's a really bad terminology. The question was, does this have anything to do with the use of the word pole, like in complex analysis? It doesn't, because a pole really means it has no, there's nothing bad that happens to it, right? So it's poorly chosen. There's a lot of cases in mathematics where we use the same word for very different things. And probably, this is not, you stop the first Riemannian geometry you meet on the street and you ask him what a pole is. He's going to say complex analysis. He's not going to think about this, right? This is a very, I don't want to say non-standard, but it's not something that comes up a lot in practice. Okay. So that's the Cartan-Hadamard theorem. That's the end of chapter 7. We're moving on to chapter 8 in Joe Carmo, which is about constant sectional curvature Riemannian manifolds. A little bit more about spaces of constant sectional curvature. I don't think we'll be able to finish this. We're definitely not going to be able to finish it today, but we'll definitely finish it on Wednesday. So he does a lot in chapter 8. I'm not going to do everything. When we say constant curvature, this always means sectional curvature. Okay. Let me remind you. So recall, mg is said to be of constant sectional curvature, little k, if k of LP is little k for all p and m, and for all two-dimensional subspaces of TPM. And this is equivalent to, if I look at the Riemann curvature tensor, and I'm just writing down what the definition is of the sectional curvature. This is equal to k for all xp, yp linearly independent in TPM. And this is equivalent to R of x, y, z, w is equal to little k times x, w, y, z minus x, z, y, w. So we did prove that if the Riemann curvature tensor had this form, then it had constant sectional curvature k. And I told you it was an if and only if, and it used the fact, which I didn't spend time talking about in chapter 4, that if you know all the sectional curvatures, it determines the Riemann curvature tensor. So this is uniquely determined if you want all the sectional curvatures to be k. And there are examples. So if we take Sn with the round metric, this has constant sectional +1. If I take Rn with the Euclidean metric, has constant sectional 0. And hyperbolic space with the hyperbolic metric, which I didn't tell you, it's in the book, you can look at it. This is n-dimensional hyperbolic space. Has constant sectional k equal -1. Okay. all of these are complete. They're all complete. You already know for the sphere and for Euclidean space that they're complete because we know the geodesics here and here, and they define for all time. Okay, and here too, you can actually compute the geodesic equation and solve it and show that the geodesics exist for all time. So I didn't show you the hyperbolic space is complete because I didn't tell you exactly what hyperbolic space is. Another remark to make here is that if the constant is not plus or minus 1 or 0, we can always rescale the metric to make it one of those. So all that really matters if you have a constant sectional curvature metric is whether that constant is positive, negative, or 0. So here's a remark. Let G be a metric on M, and let C be a positive constant. Okay, then I can define G tilde, which is C times G, is another metric. Because if I multiply a positive definite symmetric bilinear form at any point by a positive constant, it's still a positive definite symmetric bilinear form. In fact, you can do something more general here, which is multiply by an everywhere positive smooth function. That'll still be a metric. That's called a conformal. That's another metric in the conformal class. I'm doing a very special case here where the function I'm multiplying with is a constant function. Then you can see that G tilde inverse is 1 over C times G inverse. And then you can see that the Christoffel symbols are unchanged because the Christoffel symbols have a G inverse and a derivative of G. And I get a C and a C inverse and they cancel. And that means that the R, L, I, J, K tilde is the same as this one, because this guy comes by taking a derivative of gamma or a gamma times a gamma, right? And these aren't changed. And this means that R tilde I, J, K, L. So how do I go from here to the 0,4 tensor? I have to lower with the metric. I have to multiply by G tilde. That gives me a C. Okay. And hence the sectional curvature. How do I do that? I have an R tilde over a G tilde times a G tilde, because you see here, I have an R tilde and I have two, sorry, there's a square here. I have two inner products down here. So this becomes C times, this is the 0,4 tensor, right? C times the R 0,4 over a C squared G. And this is just 1 over C times K. Okay, so if I scale a metric by a constant C, the sectional curvature scales by 1 over C. So hence, up to scaling by a constant, positive constant, if MG has constant sectional curvature K, we can assume that K is either -1, 0, or +1. Okay, they're not really any different. Oh, by the way, here I should have said n at least 2, of course, right? Because this is not true if n is 1, but for any one-dimensional Riemannian manifold, they're all flat, right? So any one-dimensional Riemannian manifold has constant sectional curvature 0. We only care about our Riemannian manifolds when the dimension's at least 2. Okay, so what are we going to prove in this chapter? I've given you examples. I've told you that the actual, if it has constant sectional curvature, the actual value of the constant is not important. We can really just take it to be -1, 0, or 1. All that matters is the sign. And I've given you examples of all of these guys, which have constant sectional curvature 1, 0, -1. And I've told you they're all complete and they're all simply connected. Okay, so in this case, you see definitely I need n to be at least 2 because S1 is not simply connected. But all these spheres of dimension at least 2 are simply connected. This, of course, is simply connected. And this is diffeomorphic to Rn. by the Cartan-Hadamard theorem, Hn is diffeomorphic to Rn. So it's simply connected. Okay. Any n-dimensional space which was complete and sectional curvature constant negative has to be diffeomorphic to Rn. So I've given you examples here for everything 0, 1, and -1 of a complete and simply connected Riemannian metric of that constant curvature. And the main result of this chapter is that these are all of them. So in this section, we'll prove that if Mg is complete, simply connected, with constant sectional curvature K, in here, then M is isometric to one of those models, to one of Sn with a round metric, Rn with the Euclidean metric, or Hn with the hyperbolic metric. Okay, so up to isometry, there's only one. And it follows, this I'm probably not going to spend too much time on because it involves even more topology than I want to assume. So this in turn implies that any complete constant sectional curvature Riemannian manifold is a quotient of one of these three by a discrete subgroup of the group of isometries. Discrete subgroup of the group of isometries of the model space of the simply connected model space. Okay, so in other words, if I have a complete constant sectional curvature Riemannian manifold where the constant is positive, then by rescaling it, I can make it +1, and then it's going to be the quotient, a quotient of the round sphere by some subgroup of the group of isometries of the sphere. Isometries of the sphere are just the rotations of Rn +1, and there's going to be a discrete subgroup there whose so that you can take the quotient of this manifold. So we're not talking about taking quotients of Riemannian manifolds too much in this course, but you can do that if you have a group of isometries. You can take the quotient, and you get a Riemannian manifold, and that's what this guy will be. So up to is isometric to a quotient, and these are called space forms. It's very old school terminology, but if you hear the word space form, it means a Riemannian manifold with constant sectional curvature, and it means that it's the quotient of one of these three by a discrete group of isometries. Okay, so we're definitely going to prove this guy, and I might say a few words on Wednesday about how this goes, but involves more topology than I want to talk about. Okay. So that's the goal for the rest of today and Wednesday. How much time do I have today? 10 minutes. Well, I wonder if I have time to just state the next theorem. So before we can prove this, we need a preliminary result, which is a theorem of Cartan on the determination of the metric by the curvature. And I'm putting this in quotation marks because what do we actually mean? It's not true that if you know the Riemannian metric, the Riemann curvature tensor of some Riemannian metric, that it uniquely determines the metric. But in some sense, which I'm going to make precise in the next 10 minutes, it does. So if you know the Riemann curvature tensor in a very, very particular sense, which I'm about to describe, then it determines the metric up to isometry. Okay. And this is a tool, this has nothing to do with constant sectional curvature, and it has nothing to do with completeness either. So this is a purely local result. So since it's local, it has nothing to do with completeness. So let me state it. It'll take almost 9 minutes to state it, and then we'll prove it on Wednesday. So let's let M and M tilde be Riemannian manifolds. I guess MG and M tilde G tilde of the same dimension. There's no hope for them to be isometric if they don't have the same dimension. Let choose a point in one and a point in the other one, and let iota be a linear isometry between the tangent spaces. Be a linear isometry. So this always exists. For example, let E1 up to En be an orthonormal basis of TPM using the metric GP, and let E1 tilde up to En tilde be an orthonormal basis of TP tilde M tilde with respect to G tilde P tilde, and let I of EK be EK tilde. In fact, it always arises this way, right? If you have an isometry, then it'll take an orthonormal basis to an orthonormal basis, and vice versa. If I choose two orthonormal bases and I take the map which sends one to the other, that's a linear isometry. So there's tons of freedom there. Let's now choose let's do the following. Let V be a normal neighborhood of P such that the exponential map in M tilde of P tilde is defined on I of exp P inverse of V, which is in T P tilde M tilde. So what's going on here? It's worth the picture. So this is M, this is P, this is M tilde, this is P tilde. Let's draw TPM here. So there's some neighborhood V here, which is mapped onto diffeomorphically. I know that I can find a neighborhood of the origin in TPM, which is mapped diffeomorphically onto its image by the exponential map. Okay. And I can also apply this linear isometry I to take me into T P tilde of M tilde. So this guy is I of exp P inverse of V. And I want to make sure that the exponential map at P tilde is defined on all of this. So I can just shrink this. I know there's a neighborhood of the origin on which the exponential map of P tilde is defined. So by shrinking this guy if necessary, and then this is a bijection, that means I shrink this one, and so I shrink this one. So I can choose my normal neighborhood V of P small enough so that when I pull it back with the exponential map and I apply this linear isometry, I'm contained in a ball here on which the exponential map of P tilde is a diffeomorphism. Okay. All right. Let's see if I can state this guy. Now define a map F from this normal neighborhood V into the other manifold M tilde by F of Q is, well, I'm going to apply the inverse of XP and then iota and then XP tilde to Q for Q in V. Right? So if I have some point Q, I follow it back here and then here, and I've chosen this exactly so that I can now apply F. I can apply XP tilde to this point. Okay, so this gives me a map F, and it's clearly smooth, right? Because it's a composition of smooth maps. This is a diffeomorphism. This is linear. This is smooth. Okay. 4 minutes. I think I'm going to get to the statement. Okay, so fix a point Q in V. There exists a unique normalized geodesic gamma from 0t to m with gamma of 0 equals p, gamma of t equals q. So t is the distance from p to q. And this is just because q is in the normal neighborhood V. And let gamma tilde defined on the same interval into m tilde be the normalized geodesic on m tilde with initial point p tilde and initial velocity equal to I times the initial velocity of gamma. Okay, so gamma is some geodesic there. It has some initial velocity, gamma prime of 0, which is a tangent vector in TPM. I can map it over by I to get a tangent vector to m tilde at p tilde. So gamma tilde is the geodesic with initial point p tilde and initial velocity I of gamma prime of 0. Okay, so I can do that. So why is this defined for the same time interval? We might have to stop after that. We'll see. So note, gamma tilde is also defined up to time t. At least, right? At least. Because Q is in V, Q is gamma of t. That implies that this is equal to xp of t times gamma prime of 0. Remember, it's normalized, so this is a unit vector. But that tells us that t gamma prime of 0, this is in V, t gamma prime of 0 is equal to xp inverse of q is in xp inverse of V. So that means that I times t gamma prime of 0, which is equal to t times I gamma prime of 0 because it's linear. This is in I of xp inverse of V. So it's in the domain of xp tilde. That's how we chose V. That means I can apply so xp tilde of t I gamma prime of 0 is defined. And this equals, this is exactly the geodesic in m tilde with initial point p tilde and initial velocity gamma tilde prime at 0 at time t. So this is gamma tilde prime, gamma tilde of t. So this makes sense. Oh. Okay, so we'll have to stop here. So we'll continue next time. I'll write down all these things again, but I'm not going to go through the details of how, all these little remarks. The goal is we'll construct a given some hypotheses, which I haven't written down yet, a local isometry. Okay, essentially what it means is we have these two geodesics now, these two blue geodesics, and we're basically going to say that we're going to construct a map from here to here using these geodesics and parallel transport. I'll define it on Wednesday. And then we're going to show that if the Riemann curvature tensors evaluated on these geodesics agree in some appropriate sense, then the map we're going to define is going to end up being an isometry. Okay. So as I said, I'm out of time, so I'll continue from there on Wednesday.